Okay, so now we move into section 8.8, applications of Taylor polynomials. So in section 8.7, you learned about Taylor and Maclaurin series. And in section 8.8, you're going to learn about Taylor polynomials. And basically, a Taylor polynomial is of degree n would be the first n, well, I want to be a little careful how I phrase it, but if you take a Taylor series and use just some terms of the series, like the first 2, 3, 4 terms, something like that, that's a Taylor polynomial. Okay, so Taylor polynomials are the first, well, it's a portion of the Taylor series. That's what it is. It's not all a Taylor series, right? A Taylor series is this infinite series. It has an infinite number of terms, that power series. But if we just look at a finite number of terms of that power series, of that infinite series, we get a polynomial then. So let me give you a moment to copy this example down, and then we'll talk about it. Okay, so in this problem, we have the cube root of x. Our function of concern is the cube root of x. And on 2 point, okay. Function of concern is the cube root of x. And we're going to try to approximate, we are going to approximate that function by a second degree polynomial about a equals 8. Okay, and so the Taylor polynomial is centered about a equals 8. And then we're going to ask the question, how accurate is the approximation if x is between 7 and 9? All right, so let's go ahead and go to our formula sheet here. So the formula sheet, the part you're going to use is the part on top. Because the thing is, the cube root of x, there is no power series for the cube root of x in the table. Well, there's no Maclaurin series. So we have to derive, and actually, I want to be a little careful here. Maclaurin series are series that are centered about a equals 0. We are talking about a Taylor series, a series centered about a equals 8. So it's a Taylor series, but none of these formulas, we're going to have to use the Taylor series formula. So to use the Taylor series formula here at the top, we have to find derivatives of our function, the cube root of x. Okay, and we're going to go out how many terms? Well, if we look at this, we want a second degree Taylor polynomial. So that means we're going to go out this far to get the polynomial because we want second degree. That's the order of the polynomial. So that means we're going to have to evaluate the function and its first and second derivative at a equals 8. And then we'll put together the polynomial. So here we go. This second degree Taylor polynomial, we denote that by t sub 2 of x. That stands for a second degree Taylor polynomial. So there's the function x to the third power, that's the cube root of x. I compute the two derivatives, the first two derivatives for that function, and then I evaluate the function and the first two derivatives at a equals 8. So let me give you a moment to copy down up to here. Please let me know if you have any questions. Okay, so then the second degree Taylor polynomial about a equals 8 is given here. So it's the first three terms of a Taylor series for the cube root of x about a equals 8. I'm going to substitute in, of course, what I got for f of 8, f prime of 8, and the second derivative of f at 8. I substitute those in, those values right here, so I can construct this polynomial. Everything else is set based on the Taylor series formula. And so when we get done, this is the second degree Taylor polynomial right here. And so the cube root of x will approximately equal the second degree Taylor polynomial. But this approximation is good for values of x about close to a equals 8. Remember so all right, let me give you a moment to copy that. Okay, now what I want to do is I want to go to Desmos. And I mean, so like I'm thinking when you're doing your homework or when you're doing, your final exam and you have to type in your Taylor polynomial approximation here, you want to see if it's correct. And one way to do that, you can confirm it in Desmos. You can graph the cube root of x function, and then you can graph the second degree Taylor polynomial and see if those two functions agree within a certain range of, well, if those two functions closely approximate each other within a certain range of x values, about a equals 8. So let me show you what I did here. Let me go into Desmos. Okay, can you give me a thumbs up if you can see the Desmos okay? Is it showing up? Okay, Clea, very good. Very good, Susanna. Thank you. Thank you, Mark. So thank you, OPME. So what I did was I graphed x to the third power, and then I graphed, let me see, I don't think I want that. Yeah, I graphed x to the third power, which is the function I'm trying to approximate, and then I graphed also that second degree Taylor polynomial. And actually, let me adjust the window a little bit here, because we really, well, let me see here. Okay, so let me just see one thing here. Go to my wrench. On the y-axis, I can make a little adjustment here. I don't like to have, I like to have kind of a nice graph. And so there's a pretty good picture of, okay, so the red graph is the cube root of x, and the blue graph is that quadratic, that parabola for the second degree Taylor polynomial. So you see there at a equals 8, right at a equals 8, sorry, here. See how you have 8, 2? The polynomial is a, I want to say it's the right way. The polynomial, the Taylor polynomial and the function agree perfectly at a equals 8. The cube root of 8 is 2, and if you put 8 into the Taylor polynomial, you're going to get 2. Now, as you move away from a equals 8, do you see how the further away you move, from the value a equals 8, do you see how the polynomial approximation to this cube root function gets worse as you move away? Do you see that? And we would expect that. We would expect that. So how many of you think on maybe homework or final exam you might be using Desmos to help you confirm your answer? How many might be doing that? So maybe you get it right on the first try or the second try. How many think that's kind of a nice idea? Okay, Victoria's liking that. Good, good. So this is of course a visual confirmation that our answer is correct, but it's nice to have. Are there any questions before I go back to the problem here? All right, let's continue. Let's continue. So we have found a second degree Taylor polynomial T2, but now we want to know how accurate is this approximation for x values between 7 and 9. We can see based on the picture that, hey, it looks pretty accurate. But we need a quantitative measure. We need a quantitative value. So what we need to do is we need to use something called the Taylor's inequality. Taylor's inequality is, oddly enough, it's located in section 8.7 in your textbook. You'd think it'd be in 8.8, but it's actually introduced in section 8.7. But it's on the handout as well. That's the Taylor's inequality. So you are trying to determine what's the error, what's a bound on the error. The error is the difference between the function and your Taylor polynomial approximation. And the bound on that error is defined as m divided by n plus 1 factorial times the absolute value of x minus a to the n plus first power. Okay, that's the actual bound on the error. So this is really similar. If you think back to when you learned about numerical integration, section 5.9, you learned about like the trapezoidal rule, the midpoint rule, and so forth, and you had to find error bounds. It's the same kind of thing. We want an error bound on how well our Taylor polynomial approximates the function. But of course, what you have to find is then everything is fairly simple to find, but we need to know what m is. Well, m is greater than the absolute value of the n plus first derivative for the function. So let's see now. In our problem, we have second degree Taylor polynomial, so n is 2. So that means to determine n, we have to compute the n plus 1 derivative of f. That would be the third derivative of f. So on that note, let's go ahead and do that. Let's go ahead and do that. So how accurate is this approximation when x is between 7 and 9? We're going to use the Taylor's inequality to get an idea. R sub 2, the remainder, is equal to the difference between the Taylor polynomial and the cube root of x. Now, I guess there they define it as the cube root of x minus the Taylor polynomial. That's fine. All right, let me let you copy down up to here. Okay, let me let you copy down up to there, and then I will continue. We got to talk about this m. We have to find m. Okay, so finding m. Well, by the Taylor's inequality formula, m has to be greater than the absolute value. Okay, m has to be greater than the absolute value of the third derivative of the function. Again, it's the third derivative because we're working with the second degree Taylor polynomial. So third derivative is 3 is 2 plus 1. So, all right, I find the third derivative. That's not hard to find. We knew the second derivative. The second derivative, right, was second derivative was equal to, negative 2/9 times x to the negative 5/3 power. So the derivative of that would give us, hold on, I like things to look nice. Okay, so the derivative of that then would be 10/27 times x to the negative 8/3. Okay, so now we need to examine this third derivative. We need to examine it. We need to study it. Well, if x is between 7 and 9, then the absolute value of the third derivative is itself the third derivative because x is positive. And so the third derivative, or the absolute value of the third derivative, will be 10/27 times x to the negative 8/3 power. But that can be thought of as 10/27 times 1 divided by x to the 8/3 power. So this means that our third derivative is decreasing with x. It's decreasing with x. So to get our error bound, we want to find where that third derivative then is maximized. Okay, it's no different than when you had to find the k value for the error bounds in section 5.9. So since the third derivative, I mean, if we draw a little picture here, okay, this third derivative is decreasing. It's the absolute value of the third derivative. The third derivative is decreasing with x. So if I have a 7 and I have a 9, okay, where is the third derivative maximized? At x equals 7 or x equals 9? Good, Jonathan, at x equals 7. So that means then that m will be 10/27 times 7 to the negative 8/3 power. That's what m is going to be. So these problems in section 8.8, and I'm going to make that section available very soon to you because I want it to be available to you very soon. That generally either the derivative in question is, whether it's a third derivative, fourth derivative, in general, it's either increasing or decreasing. And of course, if you ever have a situation where you have a, hold on here, a derivative that involves that's like a cosine or a sine or a minus sine or a minus cosine, then you just take m equal to 1, m equal to 1. Because we always want m to be easy to find. But in this case, this is easy. This third derivative decreases with x, so m is maximized at x equals 7. So m is 10/27 times 7 to the negative 8/3 power. And so now we know what m is. We know what it is. And now we can find a bound on the error of our approximation. Now, the one part that you didn't see yet is what about the, well, let me just see here. So the, you have the absolute value of x minus 8 to the third power, right? So, we want the whole error bound on the right side. We want the whole error bound on the right side here to be as large as possible so that we can ensure that, I mean, we don't want to say that our approximation is more accurate than it is. So we want to be conservative and take the largest error bound possible. We found the m that's going to work, but what about this part here, this absolute value of x minus 8 to the third power? Okay, a equals 8, right? So the absolute value of x minus 8, the largest it could be would be 1. That would be when x is 7 or x is 9. So therefore, 1 is going to be what we put in there. Because 7 minus 8, absolute value of 7 minus 8 is 1, and the absolute value of 9 minus 8 is 1. And so this is going to give us then 0.00035. And so we can say that if x is between 7 and 9, the second order Taylor polynomial approximation that we found to the cube root of x is accurate to within, well, 0.00035, basically roughly 3 10,000ths, or 4 10,000ths, roughly. And this particular example from section 8.8 is actually goes with example 1 from your textbook. And these two graphs here at the bottom, these two graphs are, well, the figure 2 actually, we did that in Desmos. Figure 2, we actually went to Desmos and you saw a similar picture. That's where you have the second degree Taylor polynomial and the cube root function, and you can see that about a equals 8. It's a good approximation. And then what I've drawn here, or what actually the textbook drew in figure 3, is the error, the absolute value of the error between the two functions. That's what you have here. And you can see that if we were to take the function and subtract its second degree Taylor polynomial and graph it like in Desmos, take the absolute value of it and graph it, this is what the graph would look like. And you can see, of course, at a equals 8, the error, the remainder is 0. And then as you go away from a equals 8 to the right or to the left, the remainder or error increases, as we would expect it to. So that is that's a nice a good introductory example into section 8.8. Are there any questions on this problem? All right. Well, and certainly this will be very, very important for your final exam. Sections 8.7 and 8.8, very, very, very important. Understood, Clay. It will take time to process this. And you know, you could have learned, like if you, starting in calculus 2, you would have been able, naturally, you wouldn't have the mathematical maturity for this, but now you do, see. Now you do. So great, excellent. Are there any questions? Yatatan, we're going to talk more about section 8.8 on Wednesday, and we'll also talk about section 8.1, which is polar coordinates. We got to talk more about this section, and then we have 2 more new sections. Okay, excellent. All right. Everybody's good? Okay, let me stop the recording. Excellent.